Hello. Okay. I can just excuse myself. Sure, she would have sent it to this week.
Don't worry, give yourself. Okay.
Good afternoon, class. I hope you can hear me. For as many that have joined, please let me know if you are there. Hello. So you are welcome to CSA 221 class. And to start with, my name is Dr. Onifade from the Department of Software Engineering and at the Faculty of Computing Science and Engineering, Bafemi Awolowo University. So based on our formal knowledge on the course before us is 221 computer appreciation, and we are looking at the floating point number. So based on our knowledge on the data representation that we have done based on the last class, I'm very convinced that you have laid your hand on something reasonable on data and data representation. So today we are taking it forward to seeing what floating points numbers are and
Follow.
develop.
You press your.
Okay. So we want to look at floating point representation, and this is a way of representing an encoding number in a format that can handle very large or small values. That is, when you have a whole lot of numbers to be represented or to work with, you use floating point number representation. It is better at that, and it is based on scientific notation where numbers are represented as a fraction and as an exponent. In computing, this representation allows for trade-off between range and precision. That is, when you have a very large number, and floating is in the sense that you have a very large number. So floating points will allow us to harmonize it in such a way that it can be represented well, and in order to avoid any form of trade-off between the range, that is how large it is, then the precision, the accuracy part of it, so that when you have a very voluminous digit, floating points will allow you to work with it, and it can handle it in such a way that it will be precise. For a floating point number or real number, But just as I've said, it's just like a real number. When you have decimal point numbers, the real part of it can represent a very large value, as I've said. Like when we have 1.23 times 10 raised to the power of 88. This to tell us that when the 10 raised to the power is just like 10 raised to the power of 88, that is 10 times the number of 88 times. And when we have that, multiplying it with 1.3, it will be a very old, a very large number. And when we have a very small one, like 1.23 times 10 raised to the power of minus 88. So floating point numbers enable us to can handle all this, whether it is very big or we have the tiny part of the very small part of numbers. It could also represent very large negative number. So we can use it for both positive and negative number, and very small negative number too, as well as zero, as illustrated in the next slide. So we have this floating point number, that is the decimal numbers. So we can have from 0 to the right, at the that is very close to 0, or if it's up to infinity, that is to the right. We can have a very old number that floating point number can handle. And even to the left, as I've said, it can also cater for negative numbers, as shown in the figure, even up to minus infinity, if there's anything like that, if there are numbers that are as little, as tiny as that. So for a floating point number is typically expressed in the scientific notation with a fraction denoted by f, and an exponent which is denoted by e of a certain radius, in the form of f times f multiplied by r raised to power of e, where we have our f as fraction, in which is the exact number. The r is the base, where we have maybe base 10, base 2, and the raised to power of exponent is just the number of the degree at which any number at which we can raise any number. So decimal number use radius of 10, and which is f times 10 raised to power of e, while binary number use radius of 2, and even the 16-digit number use hexadecimal of 16. So it now depends on the base. The exponential is also raised, the radius is equivalent to the base numbers. So it depends on if you are talking about just from the residual knowledge that we had in last class. If you are talking about the binary number, you are talking about radius of 2, that is base 2. And for decimal, radius of 10 is that we are talking about decimal number, that is base 10. Representation of floating point number is not unique. For example, when we have numbers 55.66 can be represented in various ways, just like having it as 5.566 times 10 raised to the power of 1. That is, we are only taking 1. When that is raised to the power of 1, anything raised to the power of 1 is still the same number. So when we times multiplies 5.566 times 10, you still get your 55.66. Just like we can also represent it in using 0.5566 times 10 raised to the power of 2. That is, the numbers before the number before the decimal point are 2, which is 55. So using 0 to replicate that, putting 0 at the front, when we have 0.5566 times multiplied by 10 raised to the power of 2, it means that 10 raised to the power of 2 is 10, is 100, and 100 multiplied by 0.55, you still have your 55.66. So we are saying, what we are saying in essence is that the radius, the floating point is not unique for representing any number. So we can have a particular number being represented in different ways. Just like the third one, we have 0.0556 times 10 raised to the power of 10, and 10 raised to the power of 3. When you get the answer, just multiply with 0, you still have your 55.66 as what you used to have. So, and so on. So the fractional part can be normalized. That is, putting it in the right form. When you say normalization, is just to formalize, putting When you normalize, it is putting your digits or your numbers in a normal in a normal file form. So in the normalized form, there is only a single number, a single non-zero digits before the radius point. For example, we have decimal number of 123.4567 can be normalized into 1.23456 times 10 raised to power of 2, which is telling us that 1.23, we want to normalize it to have an exact number. You can see that even the numbers, when we now have 10 raised to power of 2, it means that the first number will take from from the first thing that was given 1.23.44567. Then the first number, after the first number, we have the decimal point and the raised to power of 2 will represent. So we are representing it up to in base 10. And the binary number. So please give me some time. The attendance code for the first time for the class. Please listen up. Listen up. Attendance code for the purpose of this class. For the first attendance code, we have 4H, A, 4 capital letter A, H, capital letter A, X, K. For attendance code for the first time, 4H, all in capital. So Roman, the figure 4, H, A, X, K. Do we get that? Are we getting that? Attendance number 1 is the first attendance to be taken in this class. You have 4 capital letter H, capital letter A, X for Xmas, and K. Please take note. That's your first attendance for today. So back to what we were saying. The fraction parts can be normalized, just as I've said, in order to have a more robust number. In the normalized form, there is only one single zero non-digit before the radius point. For example, when we have this, as I've said, and when you normalize it as 1.23456 times 10 raised to the power of 2 for binary number, the binary equivalence will be 1010 points. That is converting what we have in base 10 even to binary. So we have 1010.1011b, which can be normalized as given as the numbers given. Then for the format, a floating point number is typically represented as value, which is the sign. That is, the sign is to tell us whether the number is positive or negative, times the significance. The significance is also known as matrica, which will represent the precision bit of the number, and times the base. That is the base which I called radius the other time. So the base will now indicate whether it is in base, what base the number is, whether it is in base 10, base 2, base 16, and all. And the exponent is the raised power of which determine the scale of the number, whether it is raised power of 2, raised power of 3, raised power of 4, and the likes. So the need for floating point representation, for everything that we have, there is an advantage and disadvantage. So the floating point representation is crucial because, number 1, because of the range. It can represent a wide range of values from the very large to very small numbers. That is, you can say, okay, it's take care of range, like you are arranging numbers also from this to this. When you use floating point number, it will give you the exact number. So for precision, it provides a good balance between the precision, computation, graphics, and other applications where exact values and wide range are necessary. And for flexibility, it adapts to different scales of number, allow for the efficient storage and computation of real numbers on the computer system. So our number system and data representation. When you talk about number system, the floating point representation often uses binary, as I've said. It's used binary system for the digital computer because that's the language of the computer. It is either zero, it is in zeros and ones. So other number system like decimal, which is base 10, or hexadecimal base 16, may be used in different contexts. But for the purpose of the floating point number, it's used majorly, it is majorly in base 2. And data representation, this includes how number are stored in computer memory, including binary encoding and the representation of the various data type. That is, when you say you are representing data, it's bring about how number are being stored in the computer memory, which is which all boils down to binary encoding and the representation of various data type. So there are two representation schemes that we can have in this regard. We have the single 32 bits precision and for 64-bit double precision. So for 32-bit numbers, for in 32-bit single precision floating points, we have the most significant bit, which is S. That is the leftmost, the most significant, the one that are at the extreme left, with 0 for positive. So if your number, if you are given a number and the first number is 0, that is, it is positive numbers. And for 1, if the set of numbers is starting with 1, they are negative numbers. So the following 8 bits, we said we are saying 32. So the first one, the first significant bit, that is the first bit to the left, either it is 0 or 1, it depends. So it's now determine whether it is 0 or 1. If it's 0, it is positive. If it's 1, it is negative. And for the following 8 number that will follow it, the 8-bit number that will follow it, it represents the exponent, that is the base. While the remaining 22, as we have said, 1 plus 8 plus 23 to make 32 bits. So for the remaining, so it's a whole long bit of numbers that have 32. So the first one is the most significant one. The next 8 one are the exponent, while the remaining 23 bits represent the fraction. So just as I've said, looking at this figure represents it, make it clearer. That is, when we have a whole long number that is 32 bits, and the first, as is represented with X, it is the significant bit, while the exponential E is just the number of 23, and the fraction, the exponent is 8, while the remaining 23 parts will be for fraction for 32-bit single float point. And for the normalized form, for example, supposing we have the 32 bits of this number that are given in the range of 1100 and the likes. So they are in binary, that is, it is in base 2, and it is number of combination of zeros and ones. So you can see that the first significant bit is underlined as the first bit, which is the sign bit. And the number, that number 1, the one that is the first significant bit, is representing negative. That is, everything that will come out again, even after changing to decimal point, to decimal number, they are negative numbers. So, and you can see that the next one is 1100,001. It is the next one that will follow is the exponent, which is 8 in numbers, and the remaining 23 are just the fraction, just X equals 1, E equals exponential equals the next 8 digits following it, while the F take care of the remaining 23 bits. In the normalized form, the actual fraction is normalized with an implicit leading one in the form of 1 times F. That is, the leading one will be like we are saying 1 times the fraction. In this example, the actual fraction is 1.0111, like that. So which will give us this, that is 1 plus 1 times 2 raised to the power of minus 2 plus 1 plus 1 times 2 raised to the power of minus 2, and we have the decimal equivalence, which will be at the end of everything. When we do the calculation here, we have 1.375. And as we all know that from what we said about 32-bit single precision number, the first number is now determine whether it is minus, and the first number will then determine whether the numbers presented are negative or positive. So since we have the most significant bit as 1, it means that they are negative numbers. Oh yeah, and no, I dropped a message for the chat.
This one is not good. Yeah.
Yeah, I responded. Okay, I hope you can all hear me, as I've said in the chat. So some people said they can't hear, so I will try and put more volume. So just like we have in the, as I've explained it, then the next slide. We have the first one that we did was the normalized form. Then this part is the normalized form. That is when we have and he minus 7.54 32-bit floating points representing pattern like the one we have before, where we have the sign bit as the most significant bit, which is 1, as negative number, and e, which is the 0, in the the normalized form, and the fraction, which is the remaining part, which is an explicit leading O. So we have 1 multiplied by 2 raised to the power of minus 23, and the number is minus 22 raised to minus 23 by multiplied by this, and at the end we have minus 1.4 times multiplied by 10 raised to the power of minus 45. So by the time you have the material, you should be able to lay your hands on this. And for the 64 bits, the first one that we did was 32 bits, and for the 64 bits, the 64 bits scheme for 64 double precision is similar to that of 32 bits in the sense that the most significant bit, which is our x, with 0 for positive number, just as we had it in 32 bits, and 1 for negative numbers. The following 11 bits are exponents, while in 32 bits it was just 8 digits. The following bits that will be the following bits after the first one, and you have determined the first one will determine whether it is positive or negative number. So if it is 0, they are positive numbers. If it is 1, they are negative numbers. So the following 11 bits after the first one will be the exponent, just like what we had in 32 bits, whereby the following 8 bits was the exponent, while the remaining 52 bits, because we are talking about 64 here, so the remaining 62 bit represents the fraction. And just like what we have in the figure, 64-bit precision floating point number. The first significant bit out of the 64 will be for the significant the sign bit, which is the first bit on the row, on the given number. And it now depends on whether it is 0 or 1 that will now inform whether they are negative or positive numbers. And we have the exponent, which is 11 bits that will be following it. And the remaining 52 bits will now be for the fraction. For the second attendant, so please listen up. The second attendant is Zn, all in capital, Zn6Y8. Zn6Y8. So you know what to do with it. This is not your first time of being in the class. Zn6Y8. Zn6Y8. This is the second code, Zn6Y8. Zn6Y8. So you can also find it at the chart, on the chart, Zn6 Zn6Y8. That is for the second code. So, as I've said, the value n is calculated as follows. When we have the normalized form, it is for 1 less than or equals to exponent less than or equal to 2046. That's by default. And for the n, we have -1 raised to the power of x times 1.f multiplied by 2 raised to the power of e minus 102623. And the denormalized form is as given. These are in the denormalized form with the following notations. And for e exponential, which is equal to 2047 by default, n represents special value, such as whether it is positive up to as positive or negative infinity number, or not a number at all. And so there are 3 parts in floating point representation, just like we had in 32 bits. So for the 64 bits, we have the sign bits, which is the first is for 0 is the self-explanatory, as I've said before, 0 for positive numbers and 1 for negative numbers. So it depends on the ranges of number that you are being given, and what will determine the significant. The sign bit is the most significant one to the left, and you now determine what's down inform whether it is positive or negative is the first number that you are seeing there, whether it is 0 or 1. If it is 0, it is positive number. If it is 1, they are negative numbers. So for exponents, we can also call it bias or excess, is applied so as to represent both positive and negative exponent. The bias is set as half of the range. For a single precision with an 8-bit exponent, the bias is 127 by default, or SS 1.1, or SS minus 127 if it's for if it's negative. For double precision, we have with a 11 bits, the 11 bits exponent we have. So for the first one, which is 32 bits, we have 8-bit exponent with the bias of 127, whether positive or negative. So for the 64 bits, which is double precision, we have 11 bits exponents, which is the bias with 1023 for positive or excess of minus 1023. So it is either a positive or negative. Then the fraction, also called the mantissa or significant. So fractions has like three names. So we can call it fraction, we can call it mantissa or significant. It's composed of an implicit leading bit before the radius point and the fractional bit after the radius point. The leading bit for normalized number is 1, while the leading bit for the normalized number is 0. So when it is normalized, it is 1, and when it is denormalized, it is when the leading point is denormalized, it is when we have 0, the number is 0 when it is denormalized. And for the advantages of why we are using the floating point number. Number one is for wide range. That is when you have a whole lot of numbers or a whole wide range to cover. So this can represent very large and very small numbers. So it can handle whether it is the whole lot, that is, you have a wide range number, it can handle it. Whether it is too large or it is there are small numbers, and it is efficient in calculation. This is suitable for a wide range of the scientific, engineering, and graphics application where precision and range are important. When you have applications that deals with the scientific, the engineering, and the graphic, when you are dealing with graphics, and so this is efficient in the calculation and standardization. The floating point representation is standardized as 1 IEEE 754, in which this ensures consistency, compatibility across different system and programming language. So it is a standardized format. So it is across all platform, all programming language platform. And for the disadvantage, anything that has a disadvantage has the disadvantage too. So for precision issue, the floating point number can suffer from the precision errors due to rounding and truncation, because for rounding up, you have like 6.3, 6.4, if it's still less than 5, if you have it, you can still take your whole number as 6. But if it's going to like 6.5, so we now round it up to 7, which is a little bit, at least less than. There are some points that have been added to it, knowingly or unknowingly. So the precision issue is still an ongoing issue, in the sense that when you have a number and somebody will say, okay, if it's from 6.5, you have to round it up to 7. 6.5 does not mean 7, but because the precision issue, so we have to round it up in the sense that we are adding some few numbers, few figures, even to the numbers that we had, which ought not to be told. And for truncation, like you now do away with other things. Okay, like you have a whole lot of number and you now say, okay, to 3 significant bits and to 3 significant number, that is, you are counting after your decimal points. You are saying, okay, I don't want to have anything other thing to do with other numbers. So truncation, rounding off is a big issue. And number 2, complexity. The more complex than fixed point representation require more computational resources. When you have a whole lot of things to do with fixed points representation, you have to have a whole lot of computational resources to work with, and the overhead. We have operations involving the floating point numbers can be slower and require more memory compared to integer operation. Just like you are dealing with normal integer without decimal point, numbers that has no decimal point, it will be easier to process than when you have operations that involve floating point numbers, that is number with decimal point. So it will always be slower and require more memory compared to when you are dealing with integer numbers. And for the application where it is applicable, as I have said before, for scientific computation, used in simulations, used in modeling, that is, you have something that you want to replicate, you want to simulate an environment, you want to model a particular thing. And for calculations requiring the high precision and large ranges, like it is also still good when you have a whole lot of numbers that you want to work with. And so this will cater for it. And for scientific computation, for graphics, as I've said, essential in rendering and manipulating graphical data where precise calculation are needed when you have a whole lot of graphics to work with. So this is this will be very good. And in engineering, the applied in the field like the aerospace, mechanical engineering, electronics, for the accurate measurement and simulation of any form of any model that we want to bring about. Do we understand? Any question? Please make sure you fill the attendance, and I'm giving out the third one. So please try and fill it up. It's not opening. Please keep on trying. I've given out the 3 attendance codes already, so don't ask me whether you have to start or something.
And then you need to submit.
So begin to submit it right now. Submit your attendance right away. I've given out the 3 codes, and I expected you to have done it. So don't tell me the attendance has been open for attendance mark, whether it has been open or should we wait for you. So others are submitting. There is no excuse. Please submit your assignment and your attendance. The third code is Z5, ZJ6, all in capital letter. Z in capital, 5, Z, J, and 6. So see you in the next class. Thank you. And welcome back to school.
Taking the next class too.
No.